Now let us briefly understand the difference between these three people theories. Alright, first thing, in Dobby Reiner's, he arranged the elements in their increasing order of atomic mass. Next thing is he put in the three group. Another thing is that the middle elements of the mass is equal to the average of two side elements. This is what we have studied, right? Elements were arranged in increasing order, where they have put in three group like this, where the middle mass is equal to the average of both these two masses. Okay, alright, that was his theory. But when we got more elements later on in the future, we see that they were not following his theory anymore. So what about Newlands? Even Newlands, he arranged the elements in the increasing order of their atomic mass, and at elements are equal to music note show same property. That was his theory, right? After each 8 elements, okay, they show same property with the first one. Okay, now period and group was discovered by him. Period and group, the theory of period group, okay, where group used to show where group used to tell us that in that group, specific group, okay, from top to bottom, they used to show similar properties. Okay, now in Mendeleev's periodic table is that even he himself would arrange elements in their increasing order of atomic mass. He also used the theory of Mendeleev's, okay, Mendeleev's, where he took the periodic group, okay, and his main motive was he used two elements, that is hydrogen and oxygen, okay, from the hydrates and oxides formula from the other elements. Okay, he arranged his elements, finding out what kind of properties those elements have, and also he leaves some gap, okay, predicting that in the future elements were found, and in his table some empty block were kept for the elements which are yet to be found. That was his plus point. So I hope you have got it, that atomic mass were used by Newlands again from the Reiner's atomic mass, and periodic group were used by Mendeleev's. Okay, that is the plus point. All right, from one step to other step, they try to improve more, okay, as it goes on. Now lastly, over here in our modern periodic table, now here there is not a specific person name who have found this one, but why? Because there are multiple people or scientists or chemists, they are working together to form a modern periodic table, especially with the help of Mendeleev's, okay, who have done so much great work for us, okay, predicting some of the elements which are yet to be found, and shows us how this period and groups are very important. Yes, that is how we have put a modern periodic table. And here, what is the state? Modern periodic law states that the properties of elements are periodic function of their atomic numbers. In previous part, in Mendeleev's, we have seen that they were using mass. Now we are talking about atomic number. In here, in periodic table, they gave concentration to atomic number. Now what is this atomic number? If I have to ask you, then if you remember, atomic masses are what? Equal to the number of proton or the number of electron, okay, number of proton only, okay, atomic mass is the number of proton, okay, so they are concentrating in the proton. If you study about atoms from your class 9, you will still remember that atoms are made up of nuclear, proton, electrons which are out here, okay, electrons. So here, whenever they react with others, they used to either give off their electrons to others or take in electrons, right? So electrons will keep on changing, okay, keep on changing. But what happened to proton is that the number of proton will remain same even though they react or not, okay, the number of proton will remain the same. And about the atomic mass, sometimes they are very close. What happened, even though you arrange in their increasing order, they don't show similar properties anymore. But if you arrange in the increasing order of their atomic number, you'll see that some changes, like they will show similar properties, okay, and it will be much more easier for them to arrange it, and you won't find any two elements in the same block like that, okay. In earlier part over here, this is your modern periodic table. Now if you see clearly, okay, in your modern periodic table they also took the idea of group and period, okay, period. Right, period you have 1 to 7, 1 to 7. Group you have 1 to 18. Now group tell us the what types of elements, or what you can say that what kind of properties they have. All right, what kind of properties they have. All right, now if you see from the table over here, you can see that every elements are arranged in their increasing order of their what number of protons, increasing of their yes number of protons, 1 2 3. As you can see, it goes on like that. Now over here in lanthionide, okay, lanthionide or yes actinide series, over here what happened is that the continuation, okay, this series is too long that the continuation used to come over here. This does not mean it is a separate block, okay, it is the continuation over here, okay, and actinide continuation is over here called actinide series, lanthionide series, okay, it is just the continuation of it. After that you can see after 57 you got your 58 and 71, now 72, continuation is over here. Another thing, 89, 90 and 103, 104 start from here. All right, now what do you learn over here is that the first period, okay, period number 1, period, okay, this from left to right, the first period is called shortest, the shortest period, okay, the shortest period. Now from period number 3, 2 and 3 will be called as short period, okay, short period. Now from 4 to 5 will be called as long period. But when you see this one 6 and 7, okay, 6 and 7, all right, you will call them as, or no, only 6 will call as the longest period, okay, longest period. If you see the period number 7, okay, number 7, you see that there are some space over here. It shows that it is still incomplete. That is why this period will be called as incomplete period, okay, incomplete period. Now another thing you have to know is that from group, okay, see this one, group 1 is this row, group 2 is this column, okay. Now if you see this column 1 and 2, they are called S block, okay, for us to understand, okay. S block from group 3 to 12 you will call them as D block, okay, D block. And from group 13 to 18 will be called as your P block, okay, P block, sorry. Now lastly this block will be called as your F block, okay, F block. If yeah, try to understand this one. All right, now let us see the next thing. As you can see in the periodic table, first of all you will see that over here in the first group, okay, majority of the elements which are found are metals, okay, remember that they are metals. Now in your first group, let us talk about the first group, okay, 1 2, these two group are called S block, right, S block. Why we have differentiate them with other block is that this S block, okay, actually used to contain alkali and earth alkali metals, okay. The first group is called, this first group is called alkali metal. The second group is called, okay, alkali earth metal because they are found easily on earth surface, okay, earth alkali metals. Now in your D block, okay, D block, that is from 3 to 12, okay, 3 to 12 of the periodic table, they have high melting point. What block was it again? D block, okay, they have high melting point, high boiling point, okay, lots of metals are over here. Now D block behave in a manner that somewhere between the highly reactive electropositive alkali, okay, electropositive alkali, which is why they are called transition elements. This group, okay, 13 to 12, which is known as D block, are also called as transitions, over here transitional or transition metals, okay, because of their what, highly reactive electropositive alkali metal, okay, highly reactive. All right, now next is it from here 13 to 8 18, 30 to 18. This is your P block, okay, which you will see that in here you will have poor metals or no metals. This white area, okay, this white area you have your non-metals, okay, and you have your noble gas. Before I go to noble gas, can you see this area, the blue area, okay, poor metal? You have your halogen in here. In your previous topic you have seen that there were no position for halogens, but in your modern periodic table you can see that they have categorized the halogens elements over here. Halogens were what again? Halogens are those elements which have both the properties of metal and non-metal. You can see that we have lots of metals from left to right. Metals comes here, and over here you have your non-metals, and in between you have your halogens, which have both the properties of metals and non-metals. Try to remember from that way. Now when we talk about noble gas, okay, noble gas are actually those elements which have secured that their valence shells, okay, which helps them to be stable, okay, they don't react at all, okay, because their shell have become stable, and that is why we call them noble gas. And lastly over here your F block are what, rare earth metals. No wonder they are so rare, that is why they were found later on, right? Okay, now periodic table, if you want to see it clearly again, you can see your halogen category over here, okay, your halogens. All right, now before I get into the next part, for your class 10, okay, for your class 10 standard, you should know group 1 and 2 thoroughly, okay, group 13 to 18 thoroughly. Why? Because most of the question which are being asked, okay, or which will be asked, will be from group 1, 2 and group 13 to 18. So you have to know them thoroughly, okay. Now in your periodic table 2, we don't have a specific space or a specific position for hydrogen. Hydrogen is not a metal, but over here you have your metal, this hydrogen position, okay. Till now we are not certain to where we are supposed to put, but since hydrogen has number 1, okay, proton, number of proton as 1, we have put in this way, okay, in this way. So remember group 1 and 2 you have to remember thoroughly. Group 13 to 18 you have to know thoroughly, okay, to solve some of the question and answer in the later period. Okay, now in modern periodic table, since I have explained already, let us just go through. In the modern periodic table, elements are arranged in increasing order, okay, of their atomic number. Remember, atomic number, not mass anymore. We are not following mass anymore, because in the previous part those chemists and scientists, they follow atomic mass, but they concluded that they can't arrange in that method anymore. In the form, okay, now in the form of 7 horizontal rows, okay, of elements called period. 7, okay, 1 2 3 4 5 6, okay, 7 horizontal rows called period. And 18, 1 2 3 4 5 6 7, okay, 18 till 18, not rows, column, okay, column called group. Group tell us their properties, okay. This property from 18 has the property of no metal. This group tell us the metal, okay, property. This tell us halogen, okay, diagonal, it actually used to go diagonal like this, and this area, okay, this group will be non-metal. Okay, non-metal, remember that one. Now next, in your period, what is it? I've told you guys that the first period, this first period is called the shortest period, very short period. Why? Because you have only hydrogen and helium. Another thing, second period has 8 elements, lithium to neon, called short period. Okay, after, if you go another short period, long period, longest period, okay, and lastly in your 7th period you'll find that they will be called as incomplete period. All right, 14 elements, each of the 6th and 7th period are placed separately at the bottom over here. Okay, at the bottom, the 14 elements of the 6th period from continuation from lanthanide. Okay, over here the continuation is over here. Lanthanide and actinide series, they are called lanthanide and actinide series. Okay, series, remember that one. Now in group, if we talk about group, it is from top to bottom, right? There are 18 groups of elements divided into 9 main groups. Okay, 9 main groups. There are 1 2 3 to 8 and 0. Why is it like that? The group 1 to 7 has subgroups A and subgroup B. Why is it put like that? Because of that, because in this group most of it have these normal elements or metal. Okay, most of them have this metal, okay, properties. In the first group, let us see once again. Okay, the first group will be called as your alkali. Second group will be called as alkaline earth metal, because they are found on earth crust easily. Next thing are called halogens. Okay, before that it will be metal. Okay, metal, transition metal, right? Remember, next things you will get your halogens, and lastly your noble gas. Okay, now over here, why do we call noble gas here is that they have secured the outermost shells. That is why they are noble gas, where they mean that they need not have to go and react anymore. They have become stable. All right, they have become stable. Now what you will see is that in group, okay, in group they will have same number of shells. Okay, they will have the same number, no, they will have the same number of outermost electrons. Okay, valence electrons. In your period only you will see that from left to right. Okay, from hydrogen to helium, they will have the same shell. Okay, orbit. Okay, the first, in your first period you will see they will have one shell. In your second period you will see two shells. Second whole period you will see two shells. In your third period you will see three shells, and it will go on like that. Okay, so when we are talking about in a period, all the elements contain the same number of shells. Okay, that is correct. In a period, so we are talking about period. Now group. Okay, so in a period from left to right, they will show same shell. They will have same shell, number of shells. Okay, now properties of elements. In periodic group. Now what do you understand by valence electrons, or what do you understand by this valency or atomic size? Okay, let us go one after the other. Here, in a period, the number of valence electrons increases from 1 to 8 from left to right, and the number of shell is the same. Like I said earlier, again, in your periodic group, periodic table, the periods. Okay, in your periods 1 2 3 4 5 6 7, in this period number 1, from left to right. Okay, we are talking about left to right. Okay, they will have the same number of shells. Okay, just that the electrons will increase. The number of electrons will increase. You can see hydrogen has 1, helium has 2, right? So we can take the example of second period, since we have only 2 elements in the top period. Okay, so let us take the second period. You have your lithium, beryllium till neon, right? Once you arrange them, okay, 3 4 3 4 5 6 7 8, if you arrange it properly, okay, you will see 3 4 5 6 7 8 till 10, you have it right here. Even though if you arrange, okay, in your second period we said that they will have 2 orbit shells, right? Now 3 1 2 and 3, if you arrange the electrons, it will be like this. If you still remember from your class 9, the formula for arranging electrons was 2 2 8 18 32, right? In this manner you are supposed to arrange. Yes, so first shells can contain only 2, the second shell can contain till 18, the third shell can contain till 8 18 and 32. Okay, so in your first shells, 2 already done in lithium, but we still have 1 over here. Okay, so 1 2 1 2 is how you have arranged. In your beryllium you will see 4. Okay, so 2 2, if you arrange it again, the shell still remain the same, 1 2 3 4, so beryllium is 4, correct? Now if you arrange by yourself, okay, you'll see in the end neon. Okay, neon, first of all you have 2, okay, and once you put 1 2 3 4 5 6 7 8 9 10, if you calculate it, okay, the outer row can contain till 8, right? 1 2 3 4 5 6 7 8, see 8, so it makes them what? Stable, since they have acquired these stable electrons. Okay, it can cut, yes, even after putting all the numbers into it, you still have these 2 shells, right? 2 orbit shells. So we can conclude that in period, okay, from left to right, they will have the same number of shells. Alright, shells. Try to arrange by yourself again, give a try. Okay, valence electrons, the first one in lithium you see 1, the second part beryllium you have seen that there were 2. Okay, and it goes on till the end, 1 2 till the end, you will get 8. Yeah, in neon we have got 8, right? Another thing is that they had the same number of shells. Was it from left to right? You have tried it and you have found that they till the end they just had 2 number of shells. Yes, now let us see the next point. In a group, the number of valence shells is the same for all the elements, but the number of shell increases from top to bottom. So from top to bottom, like hydrogen, okay, so from top to bottom, as you go on, okay, the number from hydrogen it was 1, right? Lithium you have 2 shells. Once you go to the next one, it will become 3 shells, like that. Okay, it goes like that. So it justifies the next point, like in a group the number of valence electrons is same. Okay, it's same, valence electrons is same for all the elements, but the number of shell increases from top to bottom. All right, now when we talk about group A1, okay, group 1, if you see the number of shells, if you see from here, okay, the number of shells will keep on increasing. If you check it, okay, give a try by yourself. Alright, now let us understand what do you mean by valency. In a period, the valency of the elements increase from 1 to 4, and then decreases from 4 to 0, from the left to right. Now we are still talking about the period. Let us take the example to understand the definition. Okay, we have to take example like this from second period. Let us do again. Okay, here what was the number? If you can't see, I have written over here number of what? Atomic number. Okay, An means atomic number, that is simply as number of proton. Okay, lithium has 3, beryllium has 4, okay, till neon 8. Okay, and what we're talking about electronic configuration, right? Electronic configuration. When we talk about valency, okay, we say that it increases from 1 to 4, right? It increases to 1 to 4. What do you mean by that? Is that when we talk about lithium, okay, make the diagram again, 2 and 1. So to become stable, okay, we have come to know that the electrons in the outermost shell should have 2, in the second it should have 8, 18, 32, right? So to become stable, they should acquire this number in their outermost shells. So we can see in lithium they have only 1, and that shows that they are not stable at all. So they will go on reacting with others, they will go and react others, and to react others they will either what, accept electrons, okay, accept more electrons and become stable, okay, more electrons and become stable, or donate off electrons to others to become stable. Since they have 2 in the first shells, okay, they will become stable after donating it, okay, or they can share it. But what is the main option they can do is that if in case, okay, if they donate one off, less energy is required to do so. But if they are accepting 7 more electrons, okay, it gives off a huge stress to them, or a huge amount of energy is required to do so, okay, which is very difficult. That is why lithium used to either give off this 1 electrons to others, okay, give off electrons to others. All right, so you will see that till you'll see that lithium, beryllium till over, yeah, over here 1 to 4, after till 4 donating, okay, after see, after they have tried to donate it to others, okay, after they have tried to donate it to others, later on what happened is that the number gets reduced, right? Why did the number gets reduced? Let us talk about, okay, fluorine, okay, neon is already stable, so they do not have to react, and that is why we have put 0. They don't have to go and react because they have reached the stable shell, okay, stable. Now when we are talking about fluorine, which has 9, right, 9, let us make the diagram again. 1, 2, okay, sorry about that. 1, 2, okay, 1, 2, 3, 4, 5, 6, 7. Now if you count properly, okay, the first shell will have 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. So in this case, what happened is that they just need 1 more electrons to become stable, right? We have 7 electrons out here, 7, 8, 9, right? So we have 7 electrons out here, and to become stable, I have said that they should have either 2, 8, 18, or 32, right? So to become stable, they just need 1. That is why they will just try to accept 1, okay, accept 1 electrons is what they need, okay, they need. Else if they try to give 7 electrons to others, a huge amount of energy will be required again. So what normally they do is that they rather used to accept electrons than donating it, okay. If it is interesting, once you try to practice by yourself, okay, make the shells, make the number of electrons, remember this rules, okay, remember these rules, and try to find out the valency, okay. Valency means electronic configuration, how to become stable, okay, how to become stable. Now in here, in a group, okay, when we talk about the group, the valency is the same for all elements of the group. Why I'm saying same is that if you see from top to bottom, okay, you will see that for hydrogen they have only one, okay, one electron at the outermost, okay. When we talk about lithium, they have 2 shells, but 1, 2, 3, again 1 electrons were there in the outermost shell. When we talk about sodium, again 1, 2, 3 shells were there, right? 1, 2, how much is it? 11, right? 1 2 3 4 5 6 7 8 9 10 11. See, from top to bottom they still have 1 1, and it will goes until the bottom, right? That is what it is saying over here. It is just justifying the case, okay, the modern periodic case of how they are arranging elements, okay, justifying their rules and method. Okay, now over here, lastly, atomic size, very interesting. This is how metals used to react most of the time. So let us see the definition. What do you mean by atomic size? Atomic size means just the radius of the atom. Okay, radius, you all know what is radius. Okay, in a period, the atomic size of the elements decreases from left to right because the nuclear charge, okay, nuclear charge or number of protons increases, and so the electrons are pulled closer to the nucleus. Now again, to understand this definition, you have to first of all see the example. Okay, again we have taken the example of the second period, that is lithium to neon. Okay, lithium to neon. Now what happened is that, let me tell you that electrons have negatively charged, right? Protons have positively charged. Now these electrons will go and react, they will lose electrons or gain electrons, right? That is why protons are concentrated more. Okay, if the protons, okay, if the number of protons, important term, okay, if the number of proton is more, okay, the nuclear charge gets stronger. Now when this nuclear charge gets stronger, okay, they, proton, neutron, okay, they get the tendency or strength to pull these electrons or pull this valence closer to them, okay, closer to them. So what we can see over here is that if you see from left to right, okay, left to right, the valence shell, even though yes, the number is increasing, even if the number is increasing like this, what is happening? The size is getting decreased. The size are getting decreased. Why? Again, when the number of proton increases, okay, see number of proton like 3 4 5 6 7 8 9, when the number of proton increases, the nuclear charge, okay, nuclear charge will become stronger. Okay, once they become stronger, they get the tendency to pull the electrons in the shells, okay, closer to them. So when the shell are pulled closer to them, it will become smaller and smaller. That is how this atomic size works. Okay, that is how it is. Right now, you have seen from the example already. Now the atomic size decreases from left to right. That is what you have to know. In MCQ they used to ask, and you have to answer it in that way. Now when we talk about group, okay, in a group the atomic size of the elements increases from top to bottom. So from top to bottom the atomic size will just get on increasing. When we talk from left to right, it will decrease. When we talk from top to bottom, it will increase, the size will increase. Okay, since more valence shells are included in the periodic group, okay, the size seems to get increased. Just check out over here, okay, atomic radii, or see over here, when the number increases, the size gets reduced. And from top to bottom, why is it increasing? Why is the size increasing? Even from, if you want to see over here, okay, why is it increases? Because the number of shell used to increase from top to bottom. Yes, right, the number of shell used to get increased. That is why the size of the what shell will increase from top to bottom. Okay, from top to bottom. Now when we talk about, this is the last point over here, when we talk about metallic property, or also called as electropositive nature, okay, again, in a period the metallic property of the element decreases from left to right. Their property used to decrease from left to right. Why does their metallic properties decrease from left to right? Let us see from the example, okay, from period number 3. Now we're talking about period number 3, that is sodium to yes, argon. Now what is it? Metals, metalloid, no metal. See, metals, metalloids are halogens, and no metals is over here, and your noble gas is here. If you see in this one, in a group, the metallic property of the elements increases from top to bottom. The property, okay, the strength will increases from top to bottom, but the property will decreases from left to right. Why is that like that? Because like we said, the size used to get reduced, right? Now when the size used to get reduced, the electrons which is there in the outermost shells, okay, it gets too close, okay, it comes too close to the nuclei, okay, nuclei. The nuclear charge which is holding too tight to the electrons will prevent the electrons to go off and show this metallic property. It will prevent the electrons to go off like that. But in the leftmost side, you'll see that the size is too large. The nuclear has less proton, right? Less proton means less nuclear charge, and less nuclear charge means it will have less tendency to pull the electrons in, okay, so these electrons move around freely, showing the metallic property or electropositive property. No wonder why metal used to conduct electricity, right? Because electrons are flowing freely when we talk about the left side most area, okay, left side most area. And yeah, let us come to group, okay. Now in group, carbon is a non-metal. Look here, non-metal. Silicon is a metalloid, which is closely over here. Halogens. Germanium, okay, or yeah, is a metalloid in increasing order. As it goes on, it will increase. Metal and lead metal. That is how you have to understand, okay. Lastly, this one, non-metallic property. In non-metallic property, how do we say that substance or elements have this non-metallic property? In a period, the non-metallic property of the elements increases from left to right. Non-metallic property used to get increased because the shell used to get reduced. When that happens, electrons cannot move freely, and this electronegativity, okay, if they can't move freely means they cannot conduct electricity, okay, so we can say that non-metallic property used to increase from left to right, okay, it used to increase from left to right. If you want to see from the example with the help of period 3, okay, try it out. It is from metal, metalloid or halogens, and non-metal, okay. Now when we talk about group, in a group, the non-metallic property of the elements decreases from top to bottom. It decreases from top to bottom. Since why? Because the size of the elements, okay, shells, valence shells used to increase, right? If it decreases means non-metallic property increases, okay. But when the outermost shells increases, the non-metal property will decrease. That is how you have to remember, okay. Check the example of it again, and that's it. Thank you, everyone.